So we're going to take a break for a little bit from nodal analysis, and we're going to introduce basic mesh analysis. We'll then come back and continue working with nodal analysis, adding some other scenarios in our circuit. Right? Note that so far we've only dealt with resistors and independent current sources. So now let's look at a mesh analysis example, and notice here we also have judiciously chosen the values or the components in this initial circuit. There are only resistors and voltage sources, okay, and we'll see that that leads to the simplest mesh analysis scenario. Now make sure for a mesh circuit, for a circuit to be able to be solved by mesh analysis, the circuit has to be planar. Go back and watch that initial preliminary video where I mentioned what a planar circuit is. But this certainly is a planar circuit, and so we're going to go ahead and proceed. Now the method or the process of mesh analysis involves solving for unknown mesh currents. Recall that a mesh is a loop for which there are no loops within it. Okay, so here we have two meshes that have been identified. They are the only two meshes in this circuit, and the currents have already been labeled I1 and I2. Typically, I will label them clockwise, but you could label them counterclockwise if it was left to you to draw the currents. It's just my habit to go clockwise, and then when I do KVL around the loop, I always go clockwise as well. And the way that you solve for these mesh currents is by writing a KVL equation for each mesh. So this is completely analogous to nodal analysis, where there we were solving for unknown voltages by writing a KCL equation, summing currents at each node. Now we're going to solve for mesh current by writing a KVL equation, summing voltages around each mesh. Okay, so let's start with our first mesh I1. So we'll say KVL, I'll say at M1, mesh 1, or I1. Okay, M just stands for mesh. And I always start at the bottom left and go clockwise. So we encounter the negative sign of the 150 volts, so I'll add that in. We then, you can label voltages either way, but I'm going to label this using passive sign convention. And importantly, I want this voltage to be 20 ohms times I1, not 20 ohms times minus I1. I'm just prone to make a mistake then. So to do that, I'm going to label these voltages plus to minus going from, as I go clockwise. So I encounter the positive sign. So I'm going to write plus, and then we'll do 20 ohms times I1. And then 10 ohms times I1. Now, the current, what I really want is the current IR10. Okay, call it IR10. And so what I really should be saying here is that the voltage developed across the 10 ohm resistor is 10 ohms times IR10, right? The net current going through that resistor. But notice that that resistor is shared between both meshes, and so there's actually two currents flowing through it. There's current flowing down through it from I1, and there's a current flowing up through it, that is I2. And so the net current flowing down, as I've labeled here, IR10, is going to be equal to I1 minus I2. And this may be the most challenging conceptual part of doing mesh analysis. It's this idea of that superimposing two currents to arrive at a net current. So we have an equation already at this point, because I did the direct substitution voltage. I replaced voltages with expressions in current. We already have one equation that is expressed in terms of our two unknown currents. Let me clean this up. I'll combine the terms for I1, and that will give me 20 plus 10 ohms times I1, and then minus 10 ohms I2, and all of that is going to be equal to 150 volts. So that's the first equation here. And now let's do KVL at the second mesh. And here, I'm going to start again at the bottom left corner, and right away I encounter this 10 ohm resistor. Now, in this case, I had already labeled IR10 pointing down. Now I could do that. I could say minus 10 volts times IR10. What I would rather do is now relabel the currents, the voltage I mean, across here. Let me use a different color. Okay, we'll do purple here. So I'd like to now label the voltage across the resistor this way. And this is very analogous to when we were doing nodal analysis, that when I was doing KCL at this point, I would label current going through this 5 ohm as going from left to right. But later, when I came back and did a KCL equation at node 2, I actually relabeled current going through the 5 ohm as pointing from right to left. And that was because from the reference point of each of those nodes, the current that leaves that node actually, going through the 5 ohm resistor, is actually in two different directions, or in opposite directions, one relative to the other. Okay, so let's go back here. And so I've labeled this voltage plus and minus, and that voltage will then be 10 ohms times, and the current now will be, it'll be I2, because a positive I2 will cause a greater positive voltage according to this polarity here, the purple polarity. But if there's an increased I1, it counters that, so it's got a minus sign. Next, I encounter the 15 ohms, and that's times I2. It's the only current going through it. And then lastly, plus 100 volts, all of that equal to 0. We'll rearrange, and we'll have minus 10 ohms times I1 plus 10 ohms plus 15 ohms times I2 is equal to minus 100. And that is our second equation. We can now go back and write this in matrix form. So we can say, therefore, we would have, we're not going to have a conductivity matrix. Notice how all of these terms here are resistances. We'll actually have what's called a resistivity matrix times current. I1, I2, so this is a current vector, and that's going to be equal to some source vector, which will have a value of 150 volts and minus 100 volts. Okay, and then we have to fill in our coefficients here in the resistivity matrix. So I have 30 ohms, and I have minus 10, and I have minus 10, and then 25. Okay, and these would be ohms. And once again, you can solve for the unknown currents as the inverse of the resistivity matrix times the vector S. And that would give you the currents I1 and I2. In this case, you can also just do substitution to arrive at the final result.